As promised, now I'm going to explain the difference between conservative forces and non-conservative forces. Conservative forces are things like gravity. When something falls off a table, its potential energy turns into kinetic energy due to the work done by gravity. If it bounces up, it's going to change that kinetic energy back into potential energy. So gravity is an example of a conservative force. It conserves mechanical energy. Non-conservative forces are forces that add or remove energy from the system. For example, friction. If you're pushing a piece of furniture across the room, there's going to be friction that opposes that motion. The friction changes some of the energy into heat and vibrations and sound. So that is lost to our system of, in this case, the dresser. Also, the act of pushing the dresser is adding energy to the system. So that's also considered a non-conservative force. Any force that adds or removes energy from the system would be a non-conservative force. There's a more technical mathy definition, but we're not going to get into that here. When there's non-conservative forces, we have to add the work done by the non-conservative forces. If it's taking energy away like friction, it'll be a negative amount of work. If it's adding energy, like my pushing the dresser across the floor, it'll be a positive amount of work. So now our conservation of energy equation becomes this. Now, mechanical energy for our system is not being conserved, but energy is still being conserved globally, because even though we're adding or taking energy away, if we include as our system the whole universe, the energy is just changing from one form to another, but the total amount of energy is staying the same. So let's see how this works. This is a projectile of mass 0.75 kilograms is shot straight up with an initial speed of 18 meters per second. How high would it go if there were no air friction? Air friction, air resistance, drag, this all the same thing. So let's see. We know the mass, we know the initial speed, so we can say the initial potential energy, this is gravitational, is 0. The initial kinetic energy is 1/2 mv0 squared, which is, let's see if it's on my cheat sheet. It is not. Actually, instead of plugging in the numbers now, I'm going to leave it symbolic for now. I'm going to say the potential energy at the top is going to be mgh, where h is the height of the maximum height it reaches. That's what I'm looking for. And the final kinetic energy when it's at the peak is 0. So then when I plug it into this equation, I've got 1/2 mv0 squared equals mgh. The m's can cancel. I'm going to divide by g. H equals v0 squared over 2g, which is 16.2 meters. Now it says if the projectile rises to a maximum height of only 11.8 meters, determine the magnitude of the average force due to air resistance. So now we can say potential energy at the beginning is 0. Kinetic energy at the beginning, 1/2 mv0 squared. Potential energy at the top is mgh. That's our new height. the 11.8 meters, and the kinetic energy at the top is 0. When I plug it into this equation, I get 1/2 mv naught squared plus work non-conservative. Oh, I didn't leave enough space. Let's move that up a little. Okay, equals mgh. That's an h, not an n. I'm going to solve for the work, and then I'm going to use that work to figure out what the force is. So I'm going to subtract 1/2 mv naught squared. So the non-conservative work is going to be mgh minus 1/2 mv naught squared. And I know all those things. I can plug all those things in, and I get a work of negative 33 joules. But it doesn't ask for the work, it asks for the average force. And this is friction, so it's opposing the motion. The work non-conservative done by friction is going to be the friction force times the distance it goes, which is equal to the height. So instead of d, I'm going to write an h here. That's the new height, the 11.8 meters, times cosine of 180, because remember the friction is in the opposite direction of the motion. So the force is going to be negative work non-conservative divided by h, which is negative 33 divided by, or negative times negative, or positive, divided by 11.8. And I'm going to plug that in my calculator real quick. 2.8 newtons. Let's try another one. You can't wait to try the new water slide at Idly this summer. You climb the ladder up 5 meters. Starting from rest, you reach a speed of 4 meters per second just before you splash into the water. How much work was done by non-conservative forces if your mass is 70 kilograms? So I'm going to say the initial potential energy, now we're starting at the top of the slide. So that's going to be mgh. Notice we're just using gravitational potential energy because there's no springs here. Those are the only two we know about so far. And I'm going to just plug in the numbers. The mass is, your mass is 70 kilograms times 10 times 5 meters. And that gives us 3,500 joules. The kinetic energy starting at the top is 0 because you're starting from rest. The potential energy at the bottom is 0 because you've gone down 5 meters. And the kinetic energy at the end is 1/2 mv squared, which is 1/2 times 70 kilograms times your velocity is only 4 meters per second. 4 squared, which gives you 560 joules. So all the rest of the energy, you started with 3,500 joules, you end up with 560 joules. So the difference is going to be 560, or minus 3,500 joules. So the non-conservative forces did 2940 joules of work. They took away that much work. All the resistive forces of the friction and the water and everything took away 2,940 joules of energy. And the last problem. A basketball of mass 0.6 kilograms is dropped from rest from a height of 1.22 meters and it rebounds to a height of 0.69 meters. How much mechanical energy is lost during the collision with the floor? So our initial potential energy is mgh naught, which is 1.22 meters. And if I plug everything in, I get 7.32 joules. The potential energy, the kinetic energy at the peak is 0 because it's dropped from that point. When it hits the ground, rebounds, and comes back up, it only comes up to a height of 0.69 meters. So the potential energy it has then, mgh, is going to be a little less. It's going to be 4.14. And the kinetic energy it has on its rebound at the highest point is 0. So now we'll have a potential energy plus 0 plus the non-conservative work equals the final potential energy plus 0. So 7.32 plus WNC equals 4.14. So the non-conservative work, just have to subtract and we get negative 3.18 joules. Now, a player dribbles the ball from a height of 1.22 meters by exerting a downward force on it for a distance of 0.13 meters. You're probably familiar with this process. In dribbling, the player compensates for the mechanical energy lost during each bounce. If the ball now returns to the height of 1.22 meters, what is the magnitude of this force? So the player is doing 3.18 joules of work, adding that energy to the system because it's going to be removed by the energy lost in the bounce. So the work is going to be the force he exerts times the distance over which he exerts it times cosine. Now the force is in the same direction it's moving, so it's cosine of 0, and cosine of 0 equals 1. So if we want to know the force is just the work. This is the non-conservative. It's the only one we're talking about in this particular problem, divided by the distance. So it's positive 3.18 joules divided by 0.13 meters, which gives us a force of 24.5 newtons.